Hello everyone. In this chapter, we continue learning about the earth materials. This time we are going to focus on sedimentary rocks. Previously, when we talk about the rock cycle, we mentioned that sedimentary rocks are made of sediments generated from weathering of pre-existing rocks. Unlike igneous rocks and metamorphic rocks, all the process involved in forming sedimentary rocks does not involve super high temperature or pressure. The formation of sedimentary rocks happens near or on the Earth's surface. Sedimentary rocks make up only 5% of the Earth's crust, but it covers most of the continent. And where the Earth is covered by the sea, sediments are underlying the seawater. So even though sedimentary rocks is only a small portion of the Earth's crust, it is widely spread. And because it is widely spread, sedimentary rocks are the documentaries of ancient climate and ancient environment of the Earth. How sedimentary rocks are formed and what decides their widespreading distribution. To form sedimentary rocks, it includes the following process: weathering and erosion, transportation, deposition, and burial and lithification. I will walk you through them one by one. The source materials for sedimentary rocks are sediments from breaking down pre-existing rocks. These pre-existing rocks can be igneous rocks, metamorphic rocks, also can be sedimentary rocks. All the rocks can be broken down into smaller pieces, or for some degrees dissolved in water when they are exposed to the surface of the earth. For example, water seeps into small cracks of rocks, and when the water freezes, its volume expands. The rock will be cracked and broken into smaller pieces. This is physical weathering. Organic matter in the soils can dissolve into water, and makes the water becomes acidic, and the acidic water will dissolve some of the minerals and therefore breaks the rocks. This is chemical weathering. This weathering process generates sediments and makes the sediments easily being relocated from where they were generated. This is called weathering and erosion. Sediments will be transported by glacier, by flowing water, by wind, or by a combination of all of the means. Eventually, this transportation process will stop and the sediment ends up in a basin. This is deposition. After deposition in a basin, more sediments will continue deposit in the same basin, and the sediment that is deposited earlier will be covered by new coming sediments. And this is the process of burial. When sediment is buried, it will become compacted due to the weight loaded on top. In addition, temperature will increase as the burial depth increases. And most importantly, groundwater contains all kinds of dissolved ions, such as carbonic ion. When groundwater meets the newly buried sediments, the dissolved ions react with the sediments and forms new minerals, such as calcium carbonate. This newly formed material surrounds the sediments, just like a glue that holds all the sediment particles together. The process that forming the new material acting as a glue is called cementation. Burial plus cementation is lithification, which means that the sedimentary rock is formed. Again, let's look back. The sedimentary rock is formed from breaking down and weathering pre-existing rocks, generating sediments, then transporting the sediment and depositing in a basin. After burial and cementation, the new sediment rock is formed. The steps are weathering and erosion, followed by transportation, followed by deposition, and at last, lithification. From the last lecture, we know that to describe and classify an igneous rock, the texture and the composition of the rock is very important. This is also true for sedimentary rocks. The textures of sedimentary rock describe the size, sorting, and shape of the grains in the rock. We describe the grain size use terms like fine-grained and coarse-grained. Other than the actual size, sorting describes the variations in grain size. Well sorted means that all the grains are in similar sizes. If it is fine-grained and well sorted, that means the particle grains are all small. Poorly sorted means the grain size has a large variations. If it was a coarse-grained, poorly sorted sedimentary rock, that means though the rock is dominated by large grains, but it also contains some fine-grained mud in it. The last aspect is the shape of the grains. We use angular, subangular, subrounded, and rounded to describe the shape of the grains. The shape of the grains is related to the transportation distance. If the sediments are transported for a short distance, then the grains tend to be angular to subangular. If the sediment has experienced a long-distance transportation, then the sediments tend to be rounded or subrounded. Like we have talked about, the process of sedimentary rocks formation are very long and hard to monitor, such as weathering, transportation, deposition, and lithification. There is no way we can track all those processes, but we do care about the history of the rocks, because that is part of the history of the Earth. To study the history of the rock and the past of the Earth, we use principles of present is the key to the past. Based on observations in the present, we know that if river flows fast, it can carry a lot of sediments, and only the large gravels will stay put at the bottom of the riverbed. All the sandy materials will be carried away. If the river is small and flows slowly, the sand and mud will also be deposited in the river channel. And the sediments in the river channel will become sedimentary rocks after burial and lithification. Therefore, when we found sedimentary rocks formed in an ancient time, we look at the grain size and the grain sorting, we can know there is a big or small river. Therefore, the textures of the sedimentary rocks can tell us how the rocks were formed, such as the flow energy during deposition. I can give you more examples. Near the mountains, where topography slope is steep, water flows fast. The sediments are mostly coming directly from the mountains. The majority of them will be boulders and gravels, poorly sorted, and very angular. Following the same logic line, if we found the rocks are with gravel size, angular grains, poorly sorted, we can interpret that the rocks are formed in a near mountain alluvial environment. And this information is very helpful for paleogeography and paleoenvironment reconstruction. Similarly, in the coastal environment, a beach has abundant sun-sized sediments, and the sediments are all very well rounded and well sorted. Therefore, sedimentary rocks that is sand-sized, rounded, well sorted, can be an indicator of shoreline for the geologic past. This could help us to identify the ancient sea level change. To sum up, the textures of sedimentary rocks, besides the grain size, sorting, and roundness of the grains, the texture is determined by the transportation and the depositional energy of the sediments, and the depositional environment determines the depositional energy. Therefore, the texture can reflect the depositional environment of the sedimentary rocks, such as the near mountain alluvial environment, a river environment, or a coastal beach environment. So the texture can help us to interpret the depositional environment in the ancient past. Similar to texture, structures of sedimentary rocks can also reflect the depositional environment of the rock. Sedimentary structures are large, generally three-dimensional features of the sedimentary rocks, such as beddings, ripple marks, fossil tracks, and mud cracks. Let's talk about beddings first. Bedding, or also called stratification, is one of the most common structures of sedimentary rocks. The horizontal beddings can be formed when water is relatively quiet during deposition, such as in a big lake or in the ocean that is far away from the shoreline. Usually, when in this type of depositional environment, the sorting of the grains is usually very well. Cross-beddings can be formed when sediments are transported by a unidirectional flow fluid, such as river and wind. Wind and river can transport sediments for a long distance. Through this transportation, the roundness of the sediments can be increased, and the sorting of the grains can also be better and better during the transportation. Another structure similar to cross-beddings is ripples. Ripples are formed in unidirectional flow from rivers, but ripples are in smaller scale, in millimeters to centimeters, while cross-beddings could be in tens of meters. Ripple is an indicator of rivers. Bioturbation structures are trace fossils left behind by creatures who lived in the environment. Bioturbation structures could be root traces, worm burrows, footprints, and other traces of many living activities. They can also be indicators of depositional environments of the ancient time. Mud cracks. First of all, we know that in the present, only in very dry environment and arid climate we could have mud cracks. Therefore, if we see mud cracks preserved in the sedimentary rocks, we can also infer that the ancient environment during the rock formation is very arid. Second, we can see that the edge of the mud crack is tilting upward. This always happens when the mud dried and cracked. Therefore, in the rock record, mud cracks can also be used as an orientation pointer because tectonic events can change the original orientation of the rock and we lost the upward direction. This is very important for geologic interpretation. If there was mud cracks preserved, then the upward direction can be verified. After talking about weathering, transportation, and the deposition of sediments, now let's talk about the lithification. Lithification is a relatively complicated process. At the beginning, it requires burial. After the sediment is buried to depth, a series of physical and chemical change called diagenesis will happen to the sediments and make the loose sediments into a sedimentary rock. Let's talk about the physical change first. Burial will apply pressure to the sediments. Though this pressure compared to the pressure involved in igneous and metamorphic process are like nothing, it still can reduce the pore space between the sediments significantly. The sediments are being heavily compacted during the burial. And also there will be chemical changes. When sediments are buried to depth, groundwater with dissolved ions can react with the sediments and preserve new minerals to the remaining pore space between the sediments. The common minerals that can be formed during this process are calcite and quartz. In the picture, the area here with the yellowish color with other different color patches is where the cement is found. This newly formed mineral serves as glue to hold the sediments together, and the process is called cementation. Other chemical and biological changes involved in diagenesis, including cooking organic matters into liquid organic matter concentrates, also called fossil fuel. Because of the thermal heating from the depths of the Earth, the organic matter will stay in the remaining pore space in the sedimentary rocks. This leads to another technical question. What kind of sedimentary rocks are ideal for fossil fuel extraction? So we're going to talk about a classification of sedimentary rocks. Sedimentary rocks, including siliciclastic sedimentary rocks, chemical sedimentary rocks, and biological sedimentary rocks. The weathering, transportation, deposition, and lithification processes that we discussed are all related to siliciclastic sediments. Therefore, that's how siliciclastic sedimentary rocks are formed. The chemical sedimentary rocks and the biological sedimentary rocks are formed in different ways, but all at the Earth's surface, like siliciclastic sedimentary rocks. Let's talk about the classification of siliciclastic sedimentary rocks first. Siliciclastic sedimentary rocks are formed with the sediment. Therefore, the classification is primarily based on the grain size. In general, if the rock contains more than 10% of gravels, we call it conglomerate. If it contains mostly sand grains, then we call it sandstones. If more than 50% of the grains are mud, then we call it mudstone. If the mudstone has beddings or laminar structures, then it is called shale. Among these types of siliciclastic sedimentary rocks, conglomerate contains the most pore spaces, and the mudstones and shale contain the least. Ideally, the large pore space conglomerate would be the best rock to extract fossil fuel from, and the mudstone and shale would be the hardest to do so. However, because the conglomerates are formed near the mountains, while the mudstones and shale are formed where water is deep and quiet, such as a lake bottom and the deep ocean, where it is way more organic rich than where conglomerate is. So fossil fuel is commonly found in shale and lake, and takes a lot of effort to extract. This is how we use the characteristics of rocks to interpret depositional environment and use it as a guide to find the resources and explore the resources. In the last, I want to give you several examples of chemical sedimentary rocks and biological sedimentary rocks. Chemical sedimentary rocks are mostly formed from precipitation of minerals out of solution during evaporation or other conditions at the Earth's surface, such as gypsum rock and salt rock and dolostone. Biochemical sedimentary rocks are formed at the surface of the Earth, and it cannot be formed without biological processes. A good example is chert. Chert is a micro-sized crystal of quartz. There is a large amount of chert deposited in the deep sea, and it is formed by microbials under the sea precipitation of chert. Limestone is the most abundant biological sedimentary rocks on Earth. It can be formed in shallow marine and in lakes. The main composition of limestone is calcite. It often contains fossils. Because calcite is a soluble mineral, there is always a good portion of pore space in limestone. In addition, the shallow marine environment is also organic rich. Therefore, limestone is the reservoir rock for conventional fossil fuel. By the way, the unconventional reservoir is shale. The last common biological sedimentary rocks are coral reefs. Coral reefs is actually a type of limestone. It is special because it is formed by coral reef. Coral can build up massive reefs in shallow, warm ocean. The height of the reef keeps up with the sea level, and the creatures who lived and died in the reef environment and be preserved in the rock can also provide information about the seawater composition in the past. Therefore, sedimentary rocks can help us understand the geologic, climate history, and biological evolution and almost anything that happened at the surface of the earth. Okay, so this is all about sedimentary rocks. I hope you enjoyed this lecture and see you next time.